Okay, let's dive into this. Welcome back. Today, we're tackling a total classic and, honestly, a super satisfying puzzle in the world of dynamic programming. It's the matrix pathways problem. You know, if you've ever stared at a grid and just wondered, hey, exactly how many different ways are there to get from point A to point B, given a strict set of rules, well, you're going to absolutely love this explainer.
Here's our quick roadmap for today's explainer. First, we'll outline the matrix pathways problem. Then, we're thinking backward for solutions, establishing the base cases, populating the DP table, and finally, optimizing our space complexity.
All right, part one, the matrix pathways problem.
So imagine you're stationed right at the top left corner of an M by N matrix. Your overarching goal? Figure out the absolute total number of unique paths you can take to reach your final destination, which is way down in the bottom right corner. But of course, there's a catch. The strict constraint here is that from any given cell, you're only allowed to move in two directions, either directly down or directly right. That's it. No matter what intersection you're at, every single move inevitably pushes you closer and closer to that bottom right finish line. You just keep moving until you literally can't anymore.
Now you might be wondering, what's the best way to tackle this? The standard approach is to move forward, right? Step by step from the start. But to really crack this algorithm efficiently, I want you to completely flip your perspective. Just assume, for a second, that we've already reached that final bottom right corner. The real mystery we need to solve is, how exactly do we get here for that very last step?
Which brings us to part two, thinking backward for solutions. Think about it. If you're standing on that final target cell, there are really only two physical realities based on our movement rules. Since we can only ever travel right or down, we know for absolute certain that our very last step came from either the cell directly above us or the cell directly to our left. Those are literally the only two entry points. And guys, here is the beautiful part. This logic isn't just true for the final destination, it's equally true for practically any cell on the entire matrix. The number of paths to get to any specific cell is just the sum of the paths to the cell above it plus the paths to the cell to its left.
By breaking the matrix down like this, we've essentially uncovered what computer scientists call an optimal substructure. I know, it's a fancy term, but it's vital. It basically just means that our massive, complex main problem, finding every single path through the whole grid, can be solved simply by solving a series of much smaller, identical subproblems. Because we have to solve these tiny subproblems to get the final answer, this whole scenario is an absolutely perfect candidate for dynamic programming, or DP for short.
Now, what's really interesting about this is how smoothly that physical logic translates right into a clean mathematical formula. We can write this recurrence relation out as dp in our current row and column equals dpr-1 plus dprc-1. To put that in plain English, the total paths to our current row and column, R and C, is exactly the sum of the cell directly above it, which is row -1, plus the cell to the left of it, which is column -1. All right, moving on to part three. Establishing the base cases. So let's think about the very top row, row 0, and the leftmost column, column 0. We know for sure that starting at cell 0, 0 gives us exactly one path to itself. But what about the rest of those outer edges? Well, remember our strict rule. We can only move right or down. That means once you physically leave row 0 by stepping down, you can never go back up. There's no way. And once you leave column 0 by stepping right, you can't go back left. Because of this restriction, there is literally only one valid, straight-line path to reach any individual cell located in the topmost row or the leftmost column.
Because of that, we can safely pre-populate all those cells in row 0 and column 0 with the number 1. And this isn't just physically logical, it's actually programmatically necessary. If we just blindly applied our formula to the very top row, the code would try to check a row above it, row -1, which obviously doesn't exist. That would throw a fatal index out of bounds error and crash the whole thing. Setting these edges to 1 forms that safe mathematical foundation we really need to build the rest of our solution.
Which leads us perfectly into part 4, populating the DP table.
And this brilliantly illustrates the algorithm in action. Starting from cell 1, 1, we just apply our formula. It's super simple. 1 from the top plus 1 from the left gives us 2. Move to the right. 1 from the top plus 2 from the left gives us 3. The algorithm just sweeps through the matrix cell by cell, row by row, adding those top and left values together. The numbers cascade and accumulate perfectly until we finally hit that bottom right corner. The final value populated right there in cell dpm-1 n-1, that is our ultimate answer, the total number of unique pathways.
So, just to summarize the algorithm so far, it's really 3 easy steps.
Step 1, we set the top and left edges to 1 as our base cases. Step 2, we iterate through the rest of the grid using our addition formula. And step 3, we simply return the value held in that very last cell. It's clean, it's highly logical, and honestly, it just works flawlessly.
Okay, time for the final piece of the puzzle. Part 5, optimizing our space complexity.
Let's take a quick look at our current baseline. Our time complexity is big O of m times n. Why? Because we literally have to visit and calculate every single cell in that m by n table exactly once. That's as fast as it's going to get. We really can't optimize the time any further. However, our space complexity is also big O of m times n, because we're storing the entire two-dimensional DP table right in the computer's memory. And if that matrix is massive, yeah, that's a pretty huge memory footprint.
But wait, here's the plot twist. We are actually hoarding data we no longer need. We can completely slash our space complexity from big O of m times n all the way down to just big O of n. Sounds crazy, right? But how? Well, we just need to look a little closer at our own dependency formula.
So the crucial point is this. When calculating any given cell, the algorithm only ever looks at the cell immediately to its left and the cell immediately above it. That's it. It never looks 2 rows up. It never looks at row 0 once it's on row 2. What this means for us is that we don't actually need to keep the entire historical matrix in memory. We only ever need to maintain 2 single rows at any given time, the previous row we just finished and the current row we're actively populating. By utilizing just 2 arrays of size n, we calculate the current row, update the previous row to become our new baseline, and just discard the rest. We dramatically drop our resource footprint while getting the exact same result, a total game changer.
It really is a remarkably elegant solution to a seemingly complex problem. By thinking backward, establishing strict boundaries, and analyzing exactly what memory we actually need, we've completely mastered these matrix pathways. But right before we wrap up, I want to leave you with a little thought experiment to stretch your brain a bit further. What if the constraints suddenly changed? Like, what if some cells in the matrix were totally blocked by impassable obstacles? How exactly would you adapt this dynamic programming algorithm to navigate around them? Think about how those base cases and that simple addition formula might need to evolve. It's a fun one to ponder. Anyway, keep learning, keep optimizing, and I'll catch you in the next explainer.